So today is lab 4. We're going to do capacitors and capacitance. Does anybody know what a capacitor is or what it does? Yeah, it stores charge. Good. So capacitors store charge. All right, so here I have a circuit with a very large drawn capacitor. The battery here is going to drive a current. And the capacitor here I drew as basically two metal plates parallel to each other with a gap in between them. So as the current comes to the first plate here, what's going to happen at the plate? Does the charge have anywhere to go? No, so it's going to build up on the plate. And so since current is the movement of positive charges, even though the electrons are moving the other way, we're going to say positive charges build up on the plate, and then the absence of positive charges over here, so there's negative charges on this side of the plate. And you guys know that if there's positive charge and negative charge, that there is an electric field between the two plates. And so I drew an electric field, it goes from positive to negative. Any questions about this? So this is a schematic of what a capacitor does. Now, if a capacitor stores charge, let's say I made a capacitor and you guys made a capacitor. How will we determine whose capacitor is better? Mine. You say my capacitor. How will we know that mine's better?
Would it have a high value of capacitance?
Yes. But how will we know it has a higher value of capacitance? So it would hold more charge, right? But if I used, a 2-volt battery and I made you guys use a 1-volt battery, you guys could complain, right? That's not fair. Why do I get to use a 2-volt battery and you guys get to only get a 1-volt battery? So we define capacitance as the charge per volt. Okay? Charge per voltage. That's so that it's fair, right? Because if per 1 volt, if I hold more charge, then I'm the winner. And if for 1 volt you guys hold more charge, you guys are the winner. So this is how we define capacitance. Any questions on this? The SI unit for capacitance is farads. Its symbol is an F. A farad is actually a very, very large capacitance. In most circuits, you'll probably see something like microfarads or even picofarads are common. All right, so how do you design a good capacitor? So I have a formula here that says the capacitance is equal to epsilon naught times A over D, where A is the area of the plate and D is the distance between the plates. What's epsilon naught? Anybody know? Yeah, it's some number, 8.5 times 10 to the something. I think it's called the permittivity of free space or permeability. I always get the two confused. Is it permeability or permittivity? Permittivity, okay. And so this is in vacuum, so I put an epsilon naught there. All right, so if I wanted to make a better capacitor, what's something I could do to increase its capacitance? Good, shorten the distance, which is D here, between the two plates. If I cut D in half, right, I get twice the capacitance. So it's a good idea to have your plates as close as possible together. Of course, there's a limit. You can't make them too close together, or they might touch, and then you won't have a capacitor anymore, right? You'll just have a short circuit. Also, if it's really close together, the charges might jump the gap. And so there's a limit to how small you can make it. But in general, you want to make the gap as small as possible. What's another way to make a good capacitor? Yeah, increase the area. Make a bigger capacitor, right? More area, you can hold more charge. So if you double the area, you double the capacitance. Is there any other ways to increase the capacitance? What's that? Yeah, change something in the area in between, because right here we have epsilon naught, which is the permittivity of vacuum. But we could put another material in here which will have a different permittivity, a higher permittivity. We call those dielectric materials. Okay, and sometimes they'll write them as epsilon, which is equal to kappa epsilon naught. So kappa would be, if kappa is 2 for the material, then it increases your capacitance by a factor of 2. All right, any questions on this formula? Yeah?
So the plate material doesn't matter?
It has to be a good conductor because you have to be able to put charges on it. So metals, copper is good.
But picking one over the other doesn't change the capacitance.
Not very much. I mean, if you pick a semiconductor or something, obviously, it's going to be harder to put charges on it, so it's going to decrease the capacitance. But if we're assuming these are ideal conductors, then this formula is good. Good question. Any other questions? All right, so let's charge a capacitor. So here I have a circuit. It has a battery, has a resistor. We're familiar now with batteries and resistors. Now I'm going to put a capacitor in there. And the capacitor is two metal plates, so the symbol is just two parallel lines of equal distance. Okay. All right, so I have a circuit. How do I analyze circuits? Or what's one way to analyze a circuit? Kirchhoff's laws, yeah? Do I have a node here? I don't see any nodes, so we can't use the node rule or the node law, but we do have a loop. So let's use the loop law. And what does the loop law tell us? The sum of the voltages around a closed loop is equal to 0. All right, so I'm going to start here, and I'm going to go clockwise. The first element I hit is the battery. So I'm going to write V for the battery, voltage of the battery. The second element I'm going to hit is the resistor. So I'm going to write minus the voltage of the resistor, because by convention, everything other than the battery I'm going to call a voltage drop. That's why it gets the negative sign. The next thing I'm going to hit is the capacitor. So minus the voltage drop across the capacitor, and it all equals 0, because that's what Kirchhoff said. All right, do we know the voltage across the resistor? If we know its resistance and its current? You guys remember Ohm's law? V equals IR. So I'm going to put IR here. And then what's the voltage drop across the capacitor? This one's a little more tricky because you haven't used it as much, but you can use the definition of capacitance. So if you move V to the other side and C to the other side, you get that 1 over C times Q is equal to 0. All right. All right, so we've analyzed this circuit. We have, this equation describes the circuit. It turns out if you want to solve for Q, Q is also in the charge here. It's a differential equation. I'm not going to ask you guys to solve differential equations in here, but I will give you the answer. It's that Q as a function of time is equal to Q max 1 minus e to the minus t over tau. I'm going to box this. All right, so let's analyze this equation real quick. What happens when t is 0? We get e to the 0, which is 1. But then we got 1 minus 1, which is 0. And so at time equals 0, we have 0. So here I have q versus t. We start out at 0, which makes sense to me because if we're just starting to charge it up, at the initial time, there should be no charge on it, right? All right, what happens when t gets very large? We get e to the minus a very large number, which is a very small number, right? And so it's almost 0. So we get 1 minus almost 0 is basically 1, and we're at Q max, which makes sense. After a long, long time, the capacitor should be fully charged. So after a long, long time, it's somewhere over here, almost fully charged. And of course, in the middle, it does something like this. So that's what this equation looks like when you graph it. Any questions on this? All right, so the time constant here, tau, is the time it takes to charge the capacitor by 63.2%. So it's a measure of how long it takes to charge a capacitor. So you could say after 2 or 3 time constants, it's basically fully charged. And so if you go over here to, roughly 63.2% of Q max, and you go over here, then if you go down, this time here is tau. So this is 0.632 Q max. All right, so this would be experimentally how you determine your tau. And then we have a theoretical tau, which is tau is equal to RC, which is the resistance times the capacitance. Let's say you had a 1 farad capacitor and a 10 ohm resistor. What would be your time constant? Let's say you had a 1 farad capacitor and a 10 ohm resistor. What would be tau, your time constant? 10 seconds. So that would be your theoretical time constant. And then you can actually measure the charge versus time, get this graph, find Q max, multiply it by 0.632, and then go over and find your tau, and then compare the two. Okay? That's what you guys are going to do in this lab. Any questions on that? All right, let's discharge the capacitor. So you discharge the capacitor by taking out the battery. So I have a circuit now with no battery, just a resistor and a capacitor. Of course, this capacitor now is fully charged, so there's charge on that capacitor. So how are we going to analyze this circuit? Kirchhoff's laws. So though there's no battery, so I don't write the battery, the first thing I come to is the resistor, so I might minus the voltage of the resistor. Second guy, minus the voltage of the capacitor. And what does it equal? 0. So this is minus IR minus 1 over CQ. And again, Q is in here. It's the change in Q over time is the current, which leads us to a differential equation that I'm not going to ask you to solve, but I will give you the answer. Q as a function of time is equal to Q max e to the minus t over tau. All right, when t is equal to 0, what do we get here? We get 0 up here, which means that we got e to the 0, which is 1. And so we start out at Q max. So we're starting up here, which makes sense because we're discharging a capacitor. It starts out fully charged. What happens is t gets really large. We get e to the minus a really large number, which is very small. And so times Q max is something very small. So at large times, we're down here. And it does something like exponential decay. Looks like that. All right, if we wanted to find the time constant from here, it's a little trickier. We have to go to 100% minus 63.2% because we're discharging, which is 30, help me out, 36.8. So 0.368 of Q max. Dot, dot, dot. And that is our tau, our time constant. Any questions? All right, there's one more thing I want to tell you guys, and that's capacitors in parallel and series. Let's do parallel first. So I'm going to put a battery here. Every circuit has a resistor. put 3 capacitors in parallel. This one has capacitance C1, this one has capacitance C2, and this one has capacitance C3. And the equivalent capacitance for this is simply C1 plus C2 plus C3. So in parallel, if you want to find the equivalent capacitance of this parallel set of capacitors, what you do is simply add up the 3 capacitors. And this sort of makes sense because if you look at this equation here, what effectively you've done is you've increased the area. So each one of these has an area A, and you multiplied it by 3. So in effect, you just multiplied the area by 3 here, which increased the capacitance by a factor of 3. Does that make sense? So you just designed a bigger area capacitor by putting 3 capacitors in parallel. What about series? C1, C2, C3. Turns out for series that the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Which you might have guessed from resistors, right? One of the formulas for resistors had add up the resistors. The other one had this inverse relationship. Turns out it's opposite for capacitors because parallel has the addition for capacitors. Well, for resistors, it was the inverse relationship, and vice versa for this series. So capacitors add up the opposite of resistors. And this sort of makes sense, too, because if you put a bunch of capacitors like this, really the charge is building up on this top plate here, and minus charges are building up on this bottom plate here. And what effectively you've done, and this guy's not really doing much of anything, you just increase the distance by a factor of 3 because you got a distance here, here, and here. And when you increase the distance, it's inversely proportional to the capacitance. Any questions? All right, I want to demo this lab.